This computer. You can start, Malte.
Okay, awesome. Yeah, well, hello everyone. Today's presentation is about a term called retrieval augmented generation. It sounds very complicated. I like to think about it as adding long-term memory to large language models, be it ChatGPT or Falcon or whatever you want to name them, via document embeddings. It's going to be a mix between an architectural overview and then some fairly deep technical implementations. My goal is to show you a quick demo at the end to actually do it via a vector database called Chroma and a ChatGPT API call. So it should be around 30 minutes, but I'll keep an eye on the time, and we can speed it up or slow it down depending on how we're doing. A quick word about me. This is a quite old picture, but I currently work at a company called Redapt out of Seattle, Washington, and we mostly do Azure work for them. But this is not about me, it's about the presentation. So this is just a sort of guideline for the presentation. I might shuffle around a few slides here, but the goal is for me to start with the use case of embeddings and why they're needed. I quickly want to talk about how that use case has shifted from the early 2000s to how they're used nowadays with those large-scale LLMs. I want to touch on vector databases and why they're so important. I know Tyler has a presentation on that. I don't want to take away everything, but it might not harm to talk about one or two things more than once to really drill in the information. So I'm going to touch on a few things, Tyler, and I apologize if I take away too much, but I thought it might be helpful in that context. And then I'm going to give you a bit of background on the embeddings, sort of the main persona that invented stuff, because it's always good for trivia questions to have that knowledge. So I thought, why not? And then, yeah, a couple other topics here. Quickly talk about cosine similarity and give you some more algorithms that are used for embeddings, but I won't touch on everything because it's too much. But yeah, that's sort of the map for today. And I sort of want to get started right away with the key question, which is, what the heck are embeddings, and why do we need them? So, from my understanding, and I've been reading on this for a couple of weeks now, is that people back in the early 2000s, they were trying to solve all these natural language problems, but they were really struggling with getting human language into some unique mathematical representation. And they were trying to figure out, hey, how can we do this in the most efficient way? And they actually, let me go one step further. I'll go back to the one before, but in 2003, Bangor and Al, they coined this term embeddings because they were running a neural network on some LLM or on some NLP problem trying to solve. I think they were trying to solve, hey, given those words, predict the next word. And part of that model was this embeddings layer, which turned out to be, the coefficients or certain parameters for layer. I'll show you that architecture representation later, but essentially they were able to turn a word into a vector. And that vector was able to represent that word in a very efficient way, which will be more useful later. But that's sort of the beginning context here. Now, the requirements nowadays are that, if you have ever connected to ChatGPT, you know that if you have any input or any prompt, there's certain limits to how much you can input. So if I want to make a call to ChatGPT, I think ChatGPT 4 has a limit of 8,000 something tokens. So I cannot input the entire Bible into the prompt and get a response about it. So I have to be smart and sort of clever if I want to get information on or information about questions that have newer knowledge that the model hasn't been trained on. For example, let's say I want to get information about a person that is in the Bible, and we assume that the Bible hasn't been in the training corpora for ChatGPT. For me to get that information, I would have to either fine-tune or retrain the entire model with that Bible information. And that's very expensive and slow, and it's sort of not feasible. So what people do, they figure out, hey, I can actually take parts of that information from the Bible and embed it directly in the prompt. And that's sort of what's called prompt engineering, and it relates to the retrieval augmented generation architecture I'll show you later, because instead of having to manually embed it every time, you can take that document. So let's say you can take the entire Bible, you can chunk it into smaller pieces, and then you can embed each chunk of information and store it in a vector database. And then once you have a query, you query the database and you get the most relevant information from that database, and you embed it directly in the prompt. That might sound very complicated now, probably was, but I do have a picture that shows that in a bit better way in a second. But yeah, so the requirements for vector spaces and vector database are that the storage space should be relatively small. You don't want to store text, you want to store vectors. It should be quick to retrieve it, and you should only, you should be able to modify how many documents you want to return. And this was accomplished mostly in 2013 by Mikolov et al. They were working at Google, and they created Word2Vec, which is a toolkit that basically built upon the algorithm of Bangui et al. In 2003. And they used, I'll have a slide on this later on, but they used a couple techniques to make it faster and better. Colbert and Weston I found quite useful. They demonstrated the power of pre-trained embeddings, and that's still a very modern architecture nowadays. So 15 years ago, but still useful. I think it's quite amazing. And then Panic et al. They basically took Mikolov's Word2Vec and iterated on it and added some factual matrices on it. I'll talk about that in a second, but it's similar, but it's a smaller algorithm, so it's not as powerful, but it's better for use cases where you don't want to have a very large model and you don't have that much compute power. This is, I promise, one of the last sort of boring slides. It's the architecture of models that are out there right now. You can see that there's a lot, and there's different categories. So we have context independent and context dependent. So what that does that mean? It basically means that, do we take into account what the words mean, or do we not take into account what they mean? So on the left here, they don't take into account the meaning of the words. It just, it matters about order or how often they are in document. And then we have a separation between models that work with neural networks, so with ML or without ML, so backup words, and TF, IDF are sort of traditional encoding, should I say, algorithms that help you to, backup words. Takes, let's say you have a sentence, and it basically relates the frequency of one word to the occurrence of it. TF, IDF does that in a similar way, but it works with the entire document. And then those other three algorithms I just talked about, or Golov and Word2Vec, fast text I didn't mention, but it's similar. And then on the right, those are the more modern approaches nowadays. So I know ChatGPT uses transformers. I don't know exactly which one. That's sort of my to-do list to figure out. But yeah, it's a slightly different technique because it uses the context of the word meaning. But now I actually want to take one step back and talk about one individual piece of an embedding. So, and the goal is to take, let's say, the word cat and translate it to a vector space. So this is a very basic example of, sort of the desired output. So you have 3 words in this case, and you translate them into a 4-dimensional embedding. I'll show you how that's done later, but the ultimate goal here is that you want to take care of the sentence here. This was coined by Z.S. Harris in 1956, which means that similar words will have similar meaning. Which basically means that, if I have a word and I embed it in a vector space, a word that's similar to my embedded word should be sort of at a similar location in a vector space. And the Word2Vec algorithm was actually the first one that sort of proved that statement. And this is a very famous example from that Word2Vec algorithm. If you, take the embeddings from the algorithm and you plot them, obviously it's a multi-dimensional vector. It won't be 4-dimensional. I think Word2Vec was around 100. The modern ChatGPT embedding is around, I think, 1,530 dimensions. So it's a highly multi-dimensional space. But if you try to embed it and then visualize it, it will look something like this. So if you have the vector for men and you add the vector of gender to it, you'll end up at woman. And similarly, if you subtract or add the vector of royalty, you'll somewhere end up, I mean, it's not entirely correct, it depends on the algorithm, but you'll end up in the area of the queen, and similar goes for king. And I find that's quite fascinating because it sort of shows the underlying structure of a language in a mathematical way. And it's quite fascinating how we're able to achieve that. But yeah, so this is a good alternative. And now some, put in quotes, bad alternatives for encoding that. They aren't bad, it's too primitive to meet the goal of embedding, which is that you want to have a dense vector, and dense vector meaning, you don't want to have many zeros, which is not great for computation. And you also want to have that similar words should have similar, a similar vector in terms of orientation. So coffee and tea should be more similar than P and T. So bag of words, essentially what it does, it takes a sentence, I just mentioned it, and it basically counts the frequency of the words in that sentence and assigns a number to it. N-gram basically counts, gives you a combination of words. So for example, if you take this sentence, one encoded document would be how frequent. The next one would be frequent a word is, that will be in a 2-gram approach. So you basically take the 2 neighboring elements and put them together. And TF-IDF, again, similar to bag of words, but it's looking at the entire document in relationship to all the documents in the document database. So it's a bit more higher level than bag of words. And then you have the good old one-hot decoding approach, which basically means that if you have a vocabulary of, let's say, 5,000 words, 5,000 unique words, you'll assign a random number to each word. So you'll end up with a 5,000 dimensional vector space, which might sound feasible, but 5,000 words is very small for an natural language problem. So that's one problem. It's not really great for computational purposes. And secondly, you also don't have any similarity between vectors, because every new word, so if you were to add the 5,001st word to it, it will add a new dimension to it, and it won't be similar at all to any other words in terms of a vector space. Now, that's been solved via word2vec and all these transformer problems, and you can get embeddings nowadays super easily, so you don't really have to worry about all the underlying problems. This screenshot here is basically showing you how you can do it in OpenAI. I have that ready, so I can just run that here. So I can, create my own embedding relatively fast. You see how fast it is, and then you can see it's a very large vector. One thing maybe to point out is that you might wonder why all these values are so small. That's because they're normalized. So that's basically taking into account that all these vectors have the similar length if you take the absolute value. And we can check how long it is. I think I already did that before. Yeah, it's 1,536 dimensions, so it's quite large. And if I do, let's say, what I found is interesting, if I do house, it gives me this vector. If I do house, this you won't see, but it's actually, I checked it. It's a different vector. So it's taking into account not only word basis, you can also do sentences, which I think is cool. Not only sentences, but you can do like large paragraphs, which I'll show you in the demo in a second. Let's go back to the presentation. Okay, so we've covered that. Yeah, this is the architectural overview of the Beng-Yu et al. Piece from 2003, so the first sort of embedding model. So what they did here, they added this projection layer to the model. So they were trying to solve a very basic NLP problem back then. I think they, like I mentioned earlier, they had 5 words and were trying to predict the 6th one. And they took a vocabulary of, I don't remember how large it was, but they took a vocabulary of, let's say, 5,000 words, and they one-hot encoded each word in this input layer here. And they connected each input. So let's say, in this case, we have 3 inputs, so 3 different words. They connected each input to one activation function. So this would get 1, 2, 3 connections, and this one would get 1, 2, 3 connections. So in this case, it would be a 3x3 parameter set here on the first projection layer. So you get 9 different layers. In reality, obviously, it would be much bigger. and you most likely end up with a couple 100 millions of projection layers. And they would assign some random initialization variables to that projection layer. Same goes for the hidden layer and for the output layer. And then they would train that entire piece of algorithm here via a softmax function at the end and backpropagation. So they would basically run it, they would get an output, and they would compare it to the desired output. And they would have a loss function to backpropagate it and basically tell it, hey, you're wrong in that certain area, do it again. And they would run that until the softmax function would be minimized in terms of loss. And once it's been trained, checking the time here, you would have the projection layer, which actually is the embedding layer. So you would get the embeddings as a side product of solving an NLP problem, which I found is pretty cool. That something so important is just a side product of something not as meaningful. But yeah, so that's the overall architecture. I'm still trying to understand how the more modern versions work, but I'm working on it. So, but yeah. And yeah, so I just wanted to give you 3 more examples, or I guess I just explained one on how they are trained. So Word2Vec and Glove are sort of the more famous ones, so I'll explain those quickly. Word2Vec is, as I mentioned before, is just an improvement of this embedding layer approach here. It incorporates the continuous stack of words approach, which meaning that it basically takes a sliding window of words and sort of goes through the text instead of using one word. And it also combines a skipgram model, which is not taking a sliding window, but you're trying to predict the word by using the words around it. This actually turned out to be more efficient. You can embed larger vector spaces. So you have not only 100 dimensions, but 500 or 1,000. And you can train it on much larger corpora of text. So billions of words, which is cool and important nowadays because we want to scrape the entire internet. That scale is required there. And then Glove, again, it builds upon Word2Vec, it was built at Stanford, and it uses matrix factorization in combination with Word2Vec. I'm not that familiar with matrix factorization, I have to admit, but I know the output of it is that, so instead of using this neighboring window approach that you have at Word2Vec, it sort of uses the context of the word in this word context matrix, with statistics from the entire corpus. So I want to understand better how that's done. I might do a better presentation on this in the future, but the point of it is that it's faster to train, but not as powerful. So it's a slightly different use case. I wouldn't say it's better than Word2Vec. I would say its product market fit is slightly different, but yeah, so that's the that's all the technological background here. And I think we're 15 minutes in, so doing quite good. And now I want to sort of pivot and show you more of how these embeddings are actually used in this retrieval augmented generation approach. And this is the architecture you can see on the right. For me to really understand what's going on, I really liked, I forgot who told me that, but I think it was a YouTube video that talked about ChatGPT as sort of like a student. And you imagine that ChatGPT has an exam tomorrow on some knowledge that it doesn't know yet, and you're trying to find a way to, pass that exam. You could retrain the entire model on that knowledge. That's sort of like having a student go and take the full college class on that exam the night before, which won't be possible. Similarly, it probably won't be possible to retrain the entire model on that knowledge base. So it has to be a different way. Now you can fine tune the model, which is like retraining, but not on that scale. So you could imagine you have the student go and read the entire textbook of that class the night before. Now, depending on the student, he might do better and maybe pass it, maybe not. But ChatGPT tends to miss factual knowledge if you fine train it. You really have to do it or fine train it a lot in order to be very good at answering factual questions. And then the last option is to have the student take the exam with an open book. I mean, that's sort of like cheating, but it helps and makes it much easier to pass the exam. And you can do a similar thing with, retrieval augmented generation. That's sort of the term here. So what you actually do is you take the document of the textbook, you chunk it into smaller pieces, and each small piece you'll then run the embedding model on, and you embed that small chunk of data in your vector database. So in this case, you would embed it in Weaviate, which is a vector database provider. I'll talk about more of them in a second. But once you've embedded your entire document set, you would then run a query. Let's say you ask it, hey, answer me a question about the weather from this document. And you would take that query and you would also embed it and get a vector for it. And then you would run a cosine similarity search on that vector space here. So we basically compare your input vector to all the vectors in your database. And you'd say, hey, given this input vector, output the 3 most relevant vectors from the database. So you take those vectors, you convert them from your embedding space back to text, and you include them directly into your prompt. So it's sort of like a combination between prompt engineering and embedding. So now you have a prompt with your question and the relevant information that ChatGPT needs to answer the question. And then ChatGPT actually can go ahead and answer that question in a very likely fashion. So that's one way people found that works. And you don't need to retrain the model or fine tune it. You can simply connect it to a vector database and you have all the knowledge there. And it's quite cool because knowledge changes so frequently. Which brings me to the vector database topic. Again, Tyler's going to have a presentation on that in 2 weeks, but I just want to highlight that it's a super hot topic right now. Pinecone just had a new evaluation. They evaluated at 700 million for a super small company. Weaviate, Series A funding of 60 million the other day. Chroma, it's open source project. I think I saw the other day that they have a 1.2 star rating on GitHub, but they're still valued at 18 million, which I find funny. I don't know why their rating is so bad. I actually enjoy working with it, at least via LangChain. It's quite easy. And then I have another architectural piece here where you have the content, which is the documents. You embed them via the embedding model. You get the vectors and you put them into the database. And then you have your application, ChatGPT or any other LLM model. You query it via or you get the query, you embed the query, you get a vector, you compare the most relative. In this case, it's 3 vectors, and you get them out and you put them back to the application. So that's sort of the purpose of that architecture. Now the question is, how does it work? What I found quite fascinating is that traditional database, whatever MySQL, traditional SQL applications, usually you return matches on exact matches. So I can ask, hey, what's the weather, or give me all the rows where the date is Friday, and it will return it. Now in a vector database, that doesn't work because most likely you don't have any matching vectors. So you are finding the most similar vectors to a query. And to do that, you use a variety of different algorithms, and they are participating in a proximate nearest neighbor search. And some of these algorithms, I'll talk about them in a second, but the most famous ones are random projection, project quantization, and local sensitive hashing. And they help you to find the most relevant pieces of information to your query. And they also use hashing, quantization, and graph-based search. But yeah, again, more about that in a second. And then again, here's sort of the workflow. You have the vectors, you index them via these techniques, put them in the database, and then once you have a query, you can use these features here to post-process them in your application afterwards. Yeah, that's a very dense slide, but it shows all these algorithms in a better way, and it gives you a bit example of what they do. So you have locality sensitive hashing. It basically puts all similar vectors into the same bucket. You have product quantization. Basically compresses the size of the vectors while preserving the similarity. You have hierarchical navigable small world, which creates sort of like a graph database where each vector is connected to its nearest neighbors. So it's sort of interesting. You have hierarchical grid index, which divides the vector data space into a grid system. And then you have a ball tree index, which is the tree of nodes and leaves, and a random forest index. So the most famous examples of the algorithms that you use. And then there's examples of more vector database providers here at the bottom. But yeah, that's sort of all the underlying knowledge. What I'd like to do now is dive into the script here. And okay, so it seems to be quite long, but this is just because the text output is so long. It's actually quite simple. So the goal here is to add memory to a chain that has multiple inputs. You might wonder what a chain is, but I'm working with LangChain, which I find is a pretty cool package for interacting with ChatGPT or any large language models in that fact. They're growing pretty quickly. So if you want to work in that area, I think you should check it out. But the goal is I have this piece of text here, which is a speech from a president. It's a quite large document, so it's too large for me to embed entirely to ChatGPT. So I'll have to chunk it into, let's say, smaller pieces, and then each small piece I will embed and then store it in our database, and then I will ask a question about it, and I will embed the question, go back to the database, and get out the most relevant pieces of text, and then add them to the prompt and ask ChatGPT the question. So yeah, let's just go quickly over it. You can see here I am importing all the necessary modules. One thing here, I'm importing my OpenAI key. So if you sign up with OpenAI, they give you an OpenAI key, and you actually have to have it in your environment as a variable. Otherwise, it won't be able to authenticate. That's just something to take care of. I'm then reading the text here. So that's the text I just showed you, State of the Union. I'm splitting it into equal chunks of 1,000 tokens without any overlap. Well, this is just initiating the object, but I'm splitting it here, and I'm calling the embeddings model. If we take a look at how it's been split, you can see that here. So instead of having one large document, I now have smaller ones. So that's the first one. That's the second one, and I think there's like 20 or something like that in there. Now to me, most exciting part is the embedding piece. So it literally takes one line for me. You see, I imported the Chroma library from LangChain vector stores. And in one line, I can literally create an embedding for all these vectors here, or for all, not these vectors, for all these text pieces. So if I do this, it runs in less than 5 seconds, which is pretty cool. And now I can ask it a question. So that's my question here. What did the president, excuse me, I was disconnected. What did the president say about Justice Breyer? And then it will perform the doc search with a similarity search based on the query on that doc search I just defined here. And then it will, I'll print out some of the documents. So there's 4 in total, and yeah, you can see it worked. So I think there's something about Justice Breyer here. And then we will use that information to pass into the query, which I'll show you in a second. But that's honestly, that's more of a LangChain and prompt engineering problem. The underlying embedding problems we just solved here, which I found cool. Yeah, so this is the template that we're building. So in LangChain, they require you to work in a certain way. So usually you build a template with certain variables. In this case, we have a context variable, which that's going to be the variable or the parameter we're using to feed in the different contexts that we find from the vector search. We have a chat history variable, which we're going to use to append the history of the chat to the current template. This is useful because I want to have ChatGPT, or I want to be able to have a conversation with it. And if it forgets what I said in the input before, I find it a bit annoying. So I'm having that in there. And then I also need a human input variable here because I want to ask a question. And then the output of it, I just have to define it in a way so ChatGPT knows its role essentially. But I'm also defining the role here. So given the following extracted parts of a long document, create a final answer. I'm telling it to directly cite the text and do not rephrase any wording because I want to make sure it's correct. And then this is important because I want to have it so in case it doesn't know the answer to it, it doesn't hallucinate it. It doesn't always work, but generally speaking, it works. So it doesn't hallucinate. But yeah, I'm just defining it. I can print that prompt object. You can see it looks the same. So this is the same thing as this. Next, I just have to define a couple more LangChain objects. So I have to define the memory object. I've included some documentation about LangChain in the presentation, so you can check it out there with the 2 parameters here. And then I also have to define the Q&A chain. So LangChain chain basically is a appendment of different actions. In this case, it's first here I have to ask a question, and then I have to get the answer back. And they've automated that for me, so I don't have to go and do all the API parsing and JSON parsing from the response. And they give it to me in a nice way, and it's only 1 line, so that's why I like it. I'm defining that, and then here I can actually ask my question. So what did the president say about Justice Breyer? And I run it. And it's returning it to me right now, so which is pretty cool. And I can also ask not only factual questions, but I can also ask more semantic questions, like, for example, how was the tone of Biden's speech? And you can see, obviously, I've run it before to test, but I'm just rerunning it. And it's giving me, in this case, it's not citing the information, but it's actually analyzing it, and it's giving me an answer about it. I can also summarize the text. So I can summarize the entire speech in 3 points, and it will do it. I can also, and this is the memory piece, I can say, hey, what did I just ask you? And it does remember. And now this is the hallucination piece. So ideally, you can see the answer is already done there. But if I run it again just to prove it, it doesn't hallucinate the answer of quantum mechanics. So it doesn't think it's smarter than it is. It recognizes, hey, I don't know that from the knowledge that you've given me. And then here again, we're just checking out the entire memory of the conversation. So you can see as I execute more statements, this will grow. And at one point, I will actually hit the limit of my tokenization. So my conversation will be too long, and I probably have to cut out certain, like basically have this window be like a sliding window. I only include the last 5 points or whatever of my conversation. But yeah, so that's the demo piece. I have one more conclusion slide here. So basically this augmented generation allows you to have long-term memory in LLMs. I think vector databases are going to be quite crucial in the long term. I'm excited when the big 3 cloud providers are going to have their own personal vector databases, and if they're going to buy another one or if they're going to have their own, we're going to see. I still have, that's for my sake here, a couple open questions I want to answer, and some good tools for all of you guys to check out if you're interested to learn more about it. But yeah, so that's sort of it for today. If there are any questions, please let me know. But if not, then I hope you took away a bit of it today, at least.
Well, Malte, thank you. It was very, very good. I immediately have questions. So first question is about Chroma.
Yeah.
Which Chroma you used? Was it hosted somewhere? Like, is it your local version?
It's hosted via LangChain, so that's a cool piece. I think it's a local version, but if I go back to the code here, I don't have to install anything. I just have to connect to LangChain. So I believe they host it for me under the hood, and I don't have to do any personal hosting. I didn't install any Chroma on my machine, so it's definitely not hosted locally.
Okay. Another question is, what the size of vector embeddings in this Chroma database?
It's ChatGPT embedded, so it's this size here. It's 1536.
Whoa.
It's large. Yeah.
No, hold on. You're using ChatGPT. Which version of ChatGPT are you using?
This is ChatGPT 3 or Turbo. It's either 3 or Turbo.
No, hold on. Why? It's not ChatGPT. What is it? Text embedding ADA 002?
Oh yeah, that's OpenAI's embedding model. So it's
right.
It's not GPT's model, but I mean it's OpenAI's embedding model.
So you're using this model for your embeddings?
Yeah.
Okay, because ChatGPT itself, by the way, which version you're using ChatGPT? Is it 3 or 4?
I have to check my API call. I think it's not 4. It's either 3.5 Turbo or 3.
Okay, 3. So so you're talking about many thousands, like the dimension of vectors is much bigger than what you have here. So your chroma vectors are much smaller than ChatGPT vectors.
I'm sure I can check that out. I might look at the documentation.
No, that's fine, but it's just important to understand that your embeddings are not stored in ChatGPT. They stored separately, and they stored a different format, which is simpler than the huge model itself. Cool. And instead of chroma, you could have used, I don't know, maybe
you could use. I mean, they have. It's just this command here. So they have a variety of different vector stores, and chroma is one of them. I could have VV8 or Pinecone. They connect to all of them. I could use cognitive services and OpenAI. So in Azure that also works. But yeah, I just use chroma here because it's very simple.
Yeah, but if, for example, you have some private information, like in this speech, of course, it's not private, but let's say you have a private document. Can you still use all this technology? Like, for example, will it work if you, oh no, you use ChatGPT? I was thinking about disconnecting from the internet, but then ChatGPT will not work.
Yeah, then you have to host the LLM locally. I don't know. I think that's an architectural question in terms of how you're protecting your VNets and everything, and how you're protecting access to the database.
So I guess then you need to switch to one of the open source like Falcon 40B and install everything locally, disconnect internet. Just
I don't know. I think you can also do it in the cloud because they have it locally essentially on their end. But I would have to double check with you if that's a good question.
Malte, this is great. This presentation. Will you make this notebook available with the presentation?
Yeah, I can.
Yeah.
Yeah, I can share link.
Yeah. Does anybody else have questions?
Yeah, I have a question actually, regarding sort of how well this worked for something like the questions regarding the entire document, right? You had a couple questions in there, one like, what are the top 3 points? And one was just like, what is the tone, right? And it was interesting because none of the top 3 points were the war in Russia, right? And that was how the speech both started and ended, right? So it seems like it took chunks which were similar to the tone prompt, right? But it was missing components that referenced that, that context, right? So you're subject to maybe like selection bias in which particular chunks you actually send with your response, right? I just want to make sure I'm understanding that correctly.
Yeah, no, totally right. And I probably the prompt that I gave it wasn't the best question either. Just give it a top 3. Like that's what's it doesn't really understand, I guess, what top 3 is. I mean, it should probably from a human perspective, but you probably want to flower out.
Like needs more context.
Yeah, but yeah, that's a good point. Totally, it's never 100% accurate. Like especially I've seen pieces where even on mathematical calculations, it's giving you wrong answers from the document, which is quite funny. But yeah, it's never perfect, unfortunately, just yet.
Oh, interesting. That's very cool. Thanks.
Yeah.
There is a question in chat from Yuri.
Oh.
He asks, can you answer questions about the metadata from the document? Like, for example, when the document was created?
You would have to, not directly the way I did it, but you could grab, that information in a separate call, and I would think you can include that information in the prompt as well in a similar fashion. But yeah, so the way this works, it's not grabbing the metadata, it's just grabbing the normal data. But I think there's a way for you to pipeline out that metadata and include it in the prompt. So I think it's definitely possible. I haven't done it, but I wouldn't think it's impossible.
Okay. Any more questions? Looks to be good. Malte, thank you. This was extremely useful, and I think, well, I learned a lot myself, and I'm sure other people do too. So please send the notebook, and I'm stopping recording.